Alright, hey everyone, so welcome to day 12 of the decal. So today we are going to be covering random forests. So here's a quick agenda, the different things that we are going to be doing. So we're going to start off with this guy over here, the decision tree recap. So recall from the last lecture, the goal is we want to play a game of 20 questions with our data, and we want to pick the questions that'll maximize our information gain, and that's equivalent to maximizing our reduction of Gini impurity. And we gave a formula in the last lecture for calculating the Gini impurity for a given collection of data points with their labels. And if we run the decision tree until all of our leaves are pure, then it's very likely that we are going to overfit. So to combat this, we implement two different kinds of thresholding, either by impurity gain or by depth cutoff or both. However, decision trees are still very high variance, so one decision tree could produce variable results. So does anyone have any questions about what we covered in the last lecture? Yeah. So essentially, that's because if, let's say that I give a different subset of the data to one tree versus another, then it's variable in that way. So, that ties into overfitting. It's not very robust to changes like that, but we want a model which will be more robust in that manner. Any other questions? Do you have your hand up or you just... Okay. Yeah. So essentially what that is it's a way of calculating for a given collection of points. So let's say that I have like two different kinds of candy, red and blue. I have like 5 red and 3 blue. You don't know which is which, but you just know that distribution. So how confident would you be in randomly assigning labels? So basically, let's say that it's all red, right? On the other hand, then you could just say everything is red, right? So that has a very low amount of entropy. But on the other hand, if we have like, let's say we have 1,000 different candies, one of each, then you'd be less confident, right? So that's a measure of impurity. I recommend you go over the lecture slides and video for... I didn't see the video. Oh, yeah, the video is coming up soon, but that's going to be up tonight. But the lecture slides, because I go over some examples of calculating the impurity and more about that. And if we have time at the end, I could go over it with you if you want. Any other questions? Okay. So let's move on. So fixing high variance. So if you had to guess, so now I have a question for you. How would you say to fix this? And to give you another way of thinking about this problem, let's say that we're flipping a biased coin. We know it's more likely to be heads than tails. And someone flips that coin, reports tails, and then comes to you and says that based on that one flip, the coin is always going to be tails. What would you say in response to this person? Does anyone have any sort of ideas of what specifically the fallacy in their thinking is and what you could have them do that would get that fallacy out of their head? Anyone? Anyone? Okay. So the answer to this problem is to flip it more times. Although one observation by itself can be skewed, as the number of observation grows, it's less likely that you'll stray from the true distribution the more we flip it. So if we flip a coin that's going to be heads with 70% chance and tails with 30% chance, then if we flip the coin 1,000 times, then it's more likely that I get 700 heads and 300 tails than if I flip the coin 10 times to get 7 heads and 3 tails. Formally, we call this the law of large numbers. And you can see an example of that right here. So let's say that we just have a fair coin, and here we're graphing on the x-axis number of trials, and on the y-axis the excess heads over tails, and you can see how that tends to 0 as we go on through a number of trials. It can start out very variable over here, but it just tends to the true distribution. And you can see that over here again in a blurrier picture, where if we do this with so each of these lines is a different trial, and you can see how over time they all converge to 0%. So does anyone have any questions about this? And everyone agree with this? Okay. All right. So we've seen how it works for coins. Now, if we go back to decision trees, then we see that the solution is to just train more of them. And this is what's known as a random forest classifier. The goal of this is to train a bunch of decision trees and see how they all do. And then you do what's known as ensembling, where you have them vote. We'll see this again later when we study neural networks. And for ensembling, there are two different kinds of techniques that we can use, averaging and voting. So in averaging, we can take all of the models and feed them into a classifier, which will aggregate them in some way. It could do like a weighted average based on which one it thinks is more reliable, or just a straight up normal average. And then we have voting. We simply look at all the models and take a vote, and whichever is the majority prediction wins. Does anyone have any questions about this? Okay, so however, there is a problem with this approach just as it is. So a decision tree by itself is deterministic, because unlike with, let's say, logistic regression or linear regression or k-means or something, we don't do any sort of like random initialization, which is likely to change our result. It's just straight up based on the heuristic that whichever split maximizes information gain is likely to be the best at that moment. So if we have n-deterministic classifiers, the ensemble will be deterministic too. So how can we fix this? So I'm going to tell a little bit of a story which will help get us into this. So there's this statistician by the name of Francois Galton who did an experiment to see how effective a group of people would be at guessing the weight of an ox. He asked 800 people, and the average guess was 1,197 pounds, and that was only 1 pound off from the actual weight of 1,198. And, not everyone in the crowd knew the same amount. Like, some people had a better idea of what oxes weighed, some less. Maybe, some of them had worked with them, on a farm maybe. Some of them had read them in books, and some of them had no real idea. So you take all of those, average them, and you get something. So we can apply this philosophy of having a crowd of differing knowledges to our random forest through a process known as bootstrapping. And essentially what this is we don't give each tree the same version of our training data. Instead, we perturb it before feeding it in. And essentially what this means is we can take out some of the features, take out some of the data points, and this way we can make it so that our trees will learn differing things. And this is like Galton's ox because each tree has different knowledges and biases. And to further go on this, there are two kinds of bagging: data bagging and feature bagging. You can also do feature bagging at a node level by saying that, okay, you can only use certain features for the split, in addition to just doing it as a pre-processing step. And here you can actually see an example of this. You can you have your original data and you can bag it, and this gives some different results. Does anyone have any questions about this? Or even about anything I said previously? Okay. All right, so here we can actually see an example of a random forest for a regression problem. So here we can see we're trying to guess like the temperature, right? And so we have each of these gray lines is a different what we call weak learner, and together we can average them into a stronger learner by taking the average, and this average will do the best. It'll understand that this curve follows this sort of parabolic shape, but it doesn't overfit too much to these points over here, but it doesn't just assume a straight line and not weigh these points too heavily. So averaging a bunch of weak learners can produce a strong learner. And we can also talk about overfitting. So one remarkable thing about random forests is that they very seldom overfit. And what I mean by that is if we add more trees, it isn't going to make it more likely to overfit. If you actually want to look at the foolproof, it's like a bunch of complex math that you can look at in a paper by the inventor Leo Breiman. But we can actually talk about this intuitively with regard to the law of large numbers, right? So again, think about it as coins. The law of large numbers says that, adding more coins, we get closer to our true distribution and thus are not likely to overfit. However, adding more trees won't always increase the performance. And we can actually go back again to the law of large numbers to talk about this, because if you notice, so over here we have a big jump in our change in the ratio of heads to tails. But once we get out over here, right, you notice that flipping it more times doesn't really change it that much. So similarly, for random forests, over time, adding more trees is likely to give diminishing returns. So we don't want to, so then, then we run the risk of having our training and testing time being too unwieldy to deal with. So eventually it's better to just call it quits after a certain amount, which you can usually test for by doing cross-validation. So does anyone have any questions about this? Okay, so now we're going to dive into a different form of tree generation known as boosting. So, before when we did random forests, oh wait, actually, hold on. I'm going to back up. One thing I want to talk about before that is one advantage to random forests over decision trees is you can always get a predict probability. So, what the chances are of your class. Recall that we discussed that earlier with logistic regression. So, that by itself provides some nice advantages. However, one disadvantage that I do want to add to random forests over decision trees is that decision trees can be a lot more interpretable, right? Because one of the nice things about 20 questions is you can lay it out in a very nice, easy to display way, and that can lead to it being easy to understand. But obviously if you have a random forest, which you're just aggregating a bunch of things, then it's a lot harder to understand. So for a human to actually understand why certain decision boundaries are the way they are can be more difficult. But overall, the boost in accuracy makes up for this advantage. So now I want to talk about a slightly different way of training the forest, and that's what's known as boosting. So, before we just bagged our data, gave different features, different data points, and we were just okay, here's however many trees I have, now go train. But suppose instead that we train our trees in succession, so each tree learns from the failure of previous trees. So, that's if you get advice from someone, then you learn from their mistakes, and then if you give advice to someone, they learn from yours. So this is what's known as boosting, wherein each tree relies upon the success of the previous tree. So let's actually look at an example right here, where we have 3 decision trees, decision tree 1, 2, 3, along with the resulting tree 4. So here we see in decision tree 1, we draw this stump here. So anything in this blue side is a plus, anything red is the minus. So we're able to predict all of the minuses correctly. but we misclassify most of the pluses, getting 2 of them right. So to compensate for this in our second decision tree, what we do is the examples that we got wrong, namely these pluses, we give them a higher weight, so now we really want to get them right. So notice how now our boundary has shifted a lot to the right, because now this means we get all of our pluses right, but subsequently we get a lot more of our minuses wrong. And so now going over to decision tree 3, we draw a stump, and notice that this time it is horizontal rather than vertical, because the best line in order to predict these 3 will be a horizontal one as opposed to a vertical one. So we changed that up, and now we made sure to get these 3 minuses right, but we got this one wrong, and we got these 2 pluses wrong. But if we average them all together, we get this boundary right here. And notice how now we got everything right. This example taught us to predict these pluses correctly. This one taught us to predict these ones correctly. And this one made sure that we got the minuses correctly. So now we're able to get something which is able to predict everything correctly. However, one disadvantage to boosting over regular random forests is we can't parallelize them, especially if you're working with very large data sets. One thing you may want to do when you're training random forests is just parallelize them, train all the trees independently, and then once they're done, aggregate them all back together. But with boosting, you can't really do that so much because, again, each tree relies on the previous one. So now we actually have to train them in succession serially, which can be slow. And, again, naturally, now it's a lot more likely that we can overfit, particularly to outliers, because obviously if we have outliers that differ from the rest of our data set, then if we misclassify them by going for a more accurate decision boundary, then they'll get more weight. So that'll skew our distribution over. So keep that in mind when working with boosting versus regular random forests. Does anyone have any questions about this? Yeah?
So this is just an example, but those, for example, D1 could split more. So it wouldn't just be it could be more than just one boundary too, right?
What?
So D1?
Yeah, it could be.
Okay.
Yeah, so then, it would just be however many boundaries it would produce, because right now we just made it a simple stump. Mm-hmm. But yeah, if we wanted to, we could have drawn it out more, and then we could have had a more complex decision boundary, and then we would have averaged those. But yeah, just for the sake of simplicity, we just left it at that. Yeah? Right, so notice here in decision 2, you see how these pluses are bigger, right? So we want to make sure to weight those more correct. And so we can give those bigger weights, and that'll make sure that there's more cost to getting them wrong. Does that make sense? Okay. Any other questions? Okay, well, that was all that I have for lecture today. So I put a simple IPython notebook on GitHub where you can play around with random forests. I'll get the quiz up soon and let you guys know once I do, and then I'll get the video for the last lecture up, and I'll put the quiz link in the slides. And so I can actually work with you now more on Gini impurity.